Check, check.
Um, Hi, everyone. Welcome to this session. I'm pleased to introduce John Peach. John Peach works as a data scientist at Amazon. Outside of work, John is always learning new skills and building communities with like-minded folks in data science. John likes to mentor young people transitioning from academia to industry, and in his copious amounts of free time, he likes to fly, scuba dive, and travel with his lovely wife. He will be presenting a talk titled Careers in Data Science. Please join me in welcoming John.
Thank you very much for the lovely introduction. How are you guys this morning? Excellent. So I want to talk to you about careers in data science, the different types of data science, and then I'm going to walk through a project to give you an idea of the types of things that you do as a data scientist. So what do data scientists typically do? So our main role is to provide information around the data to business decision makers to enable them to make decisions that are based on the data. I view my role very much as one of the trusted advisor and not necessarily one as a decision maker. I try to push that back onto what I call the decision makers, and I just advise them what the data is telling me that they should do. Also, I think it's very important. I see a lot of people confuse data science with the tools. Fundamentally, at the end of the day, we're scientists, and we have a set of tools that can vary from position to position, and it's not about just using the tools, and that defines you as a data scientist. You're a data scientist, and you need to learn the right tools for the type of work that you're doing. And ultimately, at the end of the day, what we're trying to do is influence without authority. So at my job, I have a lot of influence with what production stuff happens within my organization, within Alexa. But I actually don't decide what we're going to do. I help people make those decisions. So there's many different types of data job families, and I just want to sort of quickly go over them, and then we'll dive a little deeper into different types of data science roles. So there's a business analyst, and you'll often see business analysts advertised with data science titles. Like when I'm looking at job postings, I generally ignore the title because it doesn't tell you a whole lot. You look at them, you want to be a data scientist, you're looking at them like, this doesn't describe me, but then look at another one, it describes you. So try to, when you're looking at them, look at the description, and then you can assign sort of like a label that's meaningful to you. So a business analyst translates business problems into insights. They're focused generally around key business metrics, like what's our churn rate, what's our KPIs, that type of stuff. They're really sort of analyzing the data and then spitting out numbers. They do a lot of, they're experts in business, and they try to analyze that from a business background. So if you have a background in economics or something like that, this is a great type of role for you to go in because you have that specialized knowledge. There's also business intelligence engineers. And these work a lot around defining the metrics. So they do like the weekly and the monthly business reports, that type of stuff. They build out a lot of dashboards. They do a lot of ETLs, extract, transform, load, basically pulling data from one place, reshaping it, and loading it into another place. So that's their big focus. Then you have data engineering type jobs. And these are for more the technical side of the roles. So you have a database administrator, and their job is to move and manage and maintain the data, keep the databases up and running and making them performant, but they're not necessarily doing analysis on the data. You have a database engineer who designs and builds applications sitting on top of the database. So they're very similar to a database administrator in that their core focus is just working with relational databases, but they're building things like EPR tools and enterprise resource planning tools that are heavily database focused. Then you have a data engineer. And a data engineer is basically a plumber. They build systems that move large scales of data around. So like one of the data sources that I work with at work is 50 petabytes of data. That requires specialized skills to move that type of data around, to read that type of data in a way that's performant. So that's what a data engineer does. I work closely with these people, but they don't necessarily do a lot of analysis. They help me get to the data. Then there's a new type of job that's emerging called a machine learning engineer. And really, these are specialized software developers. So most software developers know very little about machine learning. The machine learning engineer is sort of sitting between the interface between the data scientist and the software developer. Most data scientists aren't great software developers. They're scientists. And so the machine learning engineer understands enough that we can have a communication with them like, hey, I'm building the support vector machine and I'm having this problem and we need to go change the algorithm to do this. They understand enough about that they're going to be able to go and change the algorithm to make it more performant. They also do a lot of plumbing, data validation, and logging. So a lot of machine learning engineers, when a model goes into production, their job is to basically monitor that model over time to see when the model is starting to degrade with time and make the data scientist aware with it. Their job necessarily isn't to go back and refresh that model and re-engineer that model. Now, in the types of data science job families, I would classify an economist as a type of data scientist. They do the exact same things that I do, but they have a very different specialization. They're specialized in the economic side of things. And then data scientists. I'm going to talk about breaking data scientists down into different types of roles, but there's really no clear definition of what a data scientist is, right? If you want to become an engineer, a mechanical engineer. You go to university, you study mechanical engineering, you get your degree, and then you go hang out your shingle, you're a mechanical engineer. How do you become a data scientist? There's very, very few programs available. UCI down the road has an undergraduate degree in data science, but there's not many around. Like, it's people that are data scientists are coming from desperate fields and trying to figure out what this job family looks like. Fundamentally, at the end of the day, it's a mix of stats and CS. And the different types of job families I'm going to talk to you about, it's the variation in those fields that really define the definition of what type of data scientist you are. So the first one I'm going to talk about is a generalist data scientist. So this is highly specialized in math and stats. They have a generalized knowledge, typically a master's degree, but not required. And they analyze complex data sets and provide information to people, the decision makers, without necessarily the specialized knowledge that you would see. Like if you're a business analyst, you would be providing specialized business information with that. They tend to create a lot of visualizations. They drive insights within the organization. That's their main role, is to make people operate as if the decisions they're making are based off of the data. They have a basic understanding of algorithms and models. They have basic programming skills, so you don't have to have a degree in CS for this type of thing. They tend to use a lot of point-and-click tooling, and by that I mean like Tableau and stuff like that. The next type of data scientist is a research specialist, so typically a PhD in a quantitative field like chemistry, physics, engineering, neuroscience. They have a very strong background in stats. They have a background in machine learning, but they're not necessarily experts in machine learning. They use sort of the standard techniques. Their focus is on the research side of things. Their job is to take unknown problems and solve them for the organization. So they work with a lot of ambiguity, and that's the big defining characteristic of these research data scientists. Their output is usually a proof of concept. They're generally not writing production level code. It's kind of like, here's the model, and then somebody's going to go productionalize and optimize it. So their coding skills are sort of intermediate. Then you have a data scientist that is basically a machine learning specialist, so typically a PhD in computer science. They don't have a strong statistics background generally. They don't have a strong experimental background, but they are experts in machine learning. They know how to develop new algorithms, how to tune algorithms, how to deal with the different problems with different algorithms that we're using and create new ones. They have very strong coding skills, and they tend to put a lot of their code into production. So they're good at optimizing and scaling their code. So now I want to talk to you about a core skill that people should develop that I'm seeing is really lacking in university educations on key skills that you need for data science. And that's really sort of the science way of thinking. So if you go out and get a PhD, you learn to be a scientist, but nobody ever actually tells you how to be a scientist. You sort of learn through observations. And people in the design field have this concept called design thinking. And I've sort of taken design thinking and migrated that into data science design thinking as a way that you could formalize the way that a scientist learns and thinks about problems, and that will really help you land a job as a data scientist and be a very successful data scientist, because it's not about the tools, right? It's about being a scientist and the way that you think through a problem. So I'm going to talk about it by giving an example as opposed to lecturing you on the technique. So the example is based off of a project that I did for a company that hacked websites. So we were paid to hack websites. We were the good guys. And we had a problem in that we had very high customer churn. So customers would hire us. We would hack their websites. They would pay us a lot of money. And then next year, and we would find all kinds of vulnerabilities, more vulnerabilities than they could fix. And then next year, we wouldn't get a contract from them because they were like, okay, we have more vulnerabilities than we can fix. We're not going to pay you a lot of money to keep hacking our website. So how do we prevent this customer churn? So through design thinking, I want to walk you through this process. So through design thinking, there's sort of 5 components that you should be working on. Only work on one component at any one time, and don't think of this as a linear line. Like you're going to start on the left and move to the right, but you can also move back. So the first thing we want to do is we want to empathize. We want to understand what the problem is, what the customer need is. Then we want to actually very clearly define the problem. Then we want to ideate. We want to think about the problem, build some prototypes, test them, and then we're going to iterate on this very, very quickly. So empathy, we want to understand the customer's need. So in this example, we give a long list of vulnerabilities to a customer, and what the customer thought they were getting was, how do we securely maintain our websites? How do we build a security program? How do we target our efforts in fixing vulnerabilities? So a typical website will have 500 vulnerabilities. You're not going to fix 500 vulnerabilities. You're producing vulnerabilities generally faster than what you can fix them. So which ones do I fix first? Which are the important ones? Information around the different types of vulnerabilities was also very limited. It was basically, we knew the information around the vulnerabilities, but the customer really didn't. We would say that you have a cross-site scripting vulnerability here, and the customer go like, yeah, okay, thanks. I don't know what that is. So this ended up in the high churn. So in the empathy phase, what you're seeing I'm doing here is I'm really understanding what it is that the company is doing and what it is that the customer really wanted, and understanding that mishmash. And you'll see this a lot. People will pose to you a question, and then you really need to understand that. What is the basis of that question? What is it that they're really getting at? Because they often really don't know. So now you have to go through that phase of figuring out what that question really is. And there's two types of questions. So in design thinking, they use the term wicked and tame. As a scientist, I tend to use the term ill-defined and well-defined. So a wicked question is something like, how do you reduce customer churn? It's wicked because it's not answerable in an objective way. There's no clear definition of what is done. What does done look like? What is it that I'm trying to solve? How do you reduce customer churn? Does that mean I just go to one customer and say, you can have the service for free next year? I reduce customer churn, I'm done, right? That's not really what the business wants to do. So a tame or well-posed question is, what mechanisms feature would I add to give value to the customer so that they would renew, given that they have more vulnerabilities than they can fix? And I would actually take this question, I would actually define it even more and more, but it wouldn't fit into a slide. Generally, my well-posed questions are like a full paragraph long. So now I need to ideate. I need to think about what the problem is. And as a data scientist, you become an expert in an area. But you don't have to be the expert in the area to start with. So what you do is you go and you talk to the experts. So I went and I talked to our in-house hackers. I talked to top web security experts. I talked to chief information security officers. These are the guys responsible for maintaining website security and security within a corporation. I talked to the customers. What is it they wanted? What do they think that they were getting? And then I went and I talked to experts in other fields but related. There tends to be a bit of a group think when you have a problem, and it really helps to go talk to people that are in a different field but have similar problems and get the way that they think about it. Try to get as broad a scope of information as you possibly can when you're ideating and thinking about the problem. Read literature and read patents. Most problems have mostly been solved, so stop reinventing the wheel. Like, it's better to steal than it is to be completely innovative. You're much more efficient to steal. So brainstorm a lot, come up with a whole bunch of ideas, go back to the experts, put your pride aside, give them a whole bunch of ideas, and say, hey, this is good, this is not good, and get their feedback. And then go talk to experts in a different field and get their feedback, because they view the problem differently than you do. Like, you're looking for a new, novel solution. If this was simple, it probably wouldn't be on your plate. And then sleep on it. I rarely had my first idea be my best idea. So sleep on it. Build time into your process for you to think about the problem. You can be doing other things at work, but have that flexibility that you can pivot on a dime because you came up with a new idea. So my idea was, I'm going to create a security metric. So we have customer churn. My idea is I'm going to create a security metric, right? Those two things don't seem obviously linked. But from the engineering point of view, it would tell them what vulnerabilities they need to go fix. From an engineering manager point of view, it would allow them to evaluate security programs so they can determine whether or not training their employees to recognize and identify vulnerabilities and how to fix them, whether that's cost effective or not. Helps the CISOs, the Chief Information Security Officer, the guy who's ultimately responsible for security, to understand what his threat risk is. Because now he basically has this credit score, right? He understands, like, hey, you know, one's a 500, one's an 800, one's better than the other. I understand that. And executives, it's very simple for them to understand. We're going to create a metric that allows you to measure the trustworthiness of your website. Basically a FICO score, a credit score for your website. You can pitch it to them in a couple of seconds. So the idea then was, how am I actually going to do this? I'm going to create a security metric. Well, vulnerabilities, they have a very similar characteristics to statistical modeling called survival analysis. So survival analysis is grandma falls down, breaks her hips. What's the probability she'll be alive in 6 months? And there's a problem here in that grandma may die and the information gets observed, or maybe that grandma moves away and the doctor doesn't see her again and I lose information. So survival modeling is great for that. I have the same thing with vulnerabilities. A vulnerability is created, it's fixed, or a vulnerability is created and it's not fixed, or a vulnerability is created and we don't renew the contract. So I don't know what happened to the vulnerability. There's a statistical parallel around that. So I want to do a bunch of things like make it tunable by industry. I want to control behavior by using the metric. And I want to punish good behavior and punish bad behavior and reward good behavior. Freudian slip there. And this is going to do things like tell people how to get their security program, right? That was one of the things I identified early on, is people thought they were buying a security program. If they were to game the metric, they just got a security program. How long a vulnerability exists matters. So there is this concept that it's all right to create vulnerabilities, it's how quickly you fix them. And we always want to assume the worst from our customers, was one of the things that the experts suggested that we do. So now that I've ideated, I have this problem. I now have a well-defined problem. I have a general solution. I need to build a prototype. Start simple. Start at the idiotic level. What is better than what you have today, even though it's embarrassingly simple? So I'm going to start with a simple survival model. On the right-hand side is the equations. It's just a couple of simple equations. And later on, I'll show you the model that I ended up with. So basically, we have a hazard function, probability mass function, survival functions. Very, very simple. I'm just going to do the very basic, the very minimum, so I can crank something out very quickly. And then I'm going to have to go, I missed something there. Abductive reasoning is going to be a key part of the prototyping. So we're generally taught deductive reasoning. A plus B equals C, so A is equal to C minus B. Right? That's very clear and concise. But as a data scientist, you're going to work with a lot of ambiguity. So we need to do abductive reasoning, which is we need to deal with uncertainty within our data. We want to get a little better, but not necessarily perfect. So in abductive reasoning, when you're looking at your data, when you're doing your exploratory data analysis, you're going to be looking for strange things. You're going to try to understand what's happening in the data. And the bulk of your time is spent looking at your data. I mean, I jokingly say that I'm a data garbage man, because I spend 70, 80% of my time fixing, cleaning, and looking at data. And it's the little bit of modeling I do at the end is the really cool, fun stuff. But it's the abductive reasoning that I'm doing as I'm looking at this data. So I'm going to show you a bunch of graphs that I just want to point out some key concepts in. Don't necessarily have to understand the details of the graphs. So basically, along the y-axis, we have time, if you want to think it that way, when a customer started. And then along the we have time along the x-axis, and then the customer along the y-axis. So it's basically their customer number. And then whether there is a blue dot and a red dot indicating whether or not they're compliant with purchase PCI, credit card purchase information. And then if you look in 2012, there is this like vertical line that's happening here. Like, why? What happened on this day in my data that a whole pile of people changed their status for being credit card compliant or not? So you have to go and track this type of stuff down. This is really what's going to affect your models. If I didn't spend 2 weeks tracking down this problem, my model at the end of the day would have been garbage. And it's talking to experts and trying to figure out what's going on and using abductive reasoning that I was able to figure out that there was actually a code change that happened in 2012. that change the value of this field. So the data is not real. It's also really important in abductive reasoning to understand your data. So two of the big metrics you would think in determining whether a vulnerability is important or not is what's called the threat and severity. So threat is how dangerous, it's how easy it is to exploit. How much skill do you need as a hacker to exploit it? And severity is how dangerous is that threat? Like, could you be releasing private information? Could they take over control of your system? So you would think in a metric that's determined how secure your website is that these would be like the key factors in your model. And it turns out that they're not. And the reason that they're not is there's not enough dispersion within the data. So what we have here is a matrix that lists the threat and the severity. And the number of vulnerabilities determines the size of the dot. And if you look, I have one great big huge dot that is a 4 or 5. And then pretty much everything else is tiny and doesn't really matter. So there's no information in the threat and severity to tell me how dangerous vulnerabilities are because they're all dangerous, is basically the end result. So putting this in the model is actually going to be not important at all, or it's going to provide very little information. So I shouldn't build my model around this information. We also need to look at questions of scale. So we have along the bottom is the amount of time from the beginning of a scan where we're basically automated the hacking to the end of the scan. And along the y-axis is how much CPU did we use in order to do the scan. So if I have an e-commerce website, I don't want you scanning on the weekend because that's when I'm really busy. You can go scan Monday night. So guys, I don't want you to overload my system. So if it takes me a week to scan your system and you only give me 2 hours a week to scan your site, then it's going to take months and months and months to scan your system. You're not posing yourself in a position that you're allowing me to effectively do my work. So when I originally plotted the data, I had the top graph, and it looks like, hey, look, everybody does their scan really, really quickly. That's great. Don't have to worry about it. No important information there, right? Just kind of the same as what I was showing in the previous slide. So now, if I blow up that thick band on the left-hand side, I actually see something that's very different happening. I'm seeing this swooping effect within the data. I won't go into why that was happening, but it was showing a characteristic of certain behaviors that we wanted to control for. And this actually becomes a very important feature. So what was happening at a very high level was people were saying, I really don't want you to scan my website, so I'll give you an hour a week. And so now this scan is going to take 6 months to run because I don't really want you to find any vulnerabilities. Because there's a corporation wants you to, the engineering manager doesn't want you to. Because then he has to go fix it. He doesn't get paid to fix vulnerabilities. He gets paid to release product. So some more abductive reasoning. So that led me to think about, like, well, why is that happening? Like, that doesn't make any sense. They're paying us a lot of money to scan their website. So we have 3 different products, PE, SE, and BE. So BE is the basic edition. SE is sort of the middle class edition. PE is the professional edition. And this, you pay a lot of money for PE. So PE generally requires us to authenticate to a website in order to scan it, right? So if you go to Facebook and you don't log in, you're just going to scan the login page all day long, right? You're not really assessing any vulnerabilities there. So the top graph shows the number of sites that required authentication. So pretty much every PE site required authentication. The bottom graph shows the number of sites that we actually had authentication information for. And we have this huge chunk, the red chunk at the bottom in this graph here, basically is saying we don't have authentication information for these websites. Why? And it turns out the managers didn't want us scanning. So basically, they were paying us a ton of money to scan their login web page, and they fixed the vulnerabilities on the login web page. So now that they report we have no vulnerabilities, we can go ahead and release our features. So now that I've done all this diving into the data and understanding, I need to build prototypes. So I'm going to use the knowledge from the experts. I'm going to use the knowledge that I've gained from looking at the data, using my abductive reasoning to figure out what's going on, talking to the customers. Now I'm going to clean my data. Spend a lot of time cleaning my data. And I'm going to do this in a way that's reproducible. A lot of people sort of do stuff, throw it away, do stuff, throw it away. I do everything, so I could hand it over to somebody tomorrow and they could reproduce everything that I did. If I got x equals 5, they know exactly where that 5 comes from. Every data source is logged, every piece of code is logged, every graph that I have, I keep. I generate hundreds and hundreds of graphs, I keep them all. And I have it in a very organized document that I use for me. Then I go and I build a very, very simple model, the null model. I take the average, something idiot-proof. And then I build complexity on the models. So I do that through testing. I build a prototype, very simple. I then test it. And so people are like, well, but you have a really bad model. George Box of the famous box plot and so much more, he one time has a quote associated with him that says, all models are wrong, but some are useful. I keep that in the back of my head. Everything that I do is wrong, but is it useful? Is the null model better than not knowing anything? If it is, it's a good model. I can probably do better. I hope I can do better. But it's better than what I have. So now I'm going to test this. I have a hypothesis around it. I'm going to learn from the test very quickly. I'm going to learn like, hey, the null model gets me 90% of the way there. I'm done. I'm going to go do something else. I could spend the next 6 months getting 95% of the way there, but I could go do something else and have more impact. Or I could say like, hey, my model is at 10%. I think this is the opportunity space. And then I can go get support from leadership, go back and develop another hypothesis, build another prototype, and move on. So it's very, very much a rinse and repeat. I don't build one model. I build dozens, if not hundreds of models. And in the model building phase, I want to test the importance of something. So one of the things we had was we tracked originally whether vulnerability was created and whether it was fixed, but that same vulnerability can be created again. So we had the way the data was stored. We knew when it was first created, we knew when it was last fixed, but we didn't know the intermediate in between. We had that data. It was really, really hard to get at. So I said, well, that sounds like it's really important information. Like it seems to make sense. If you're fixing a vulnerability and then recreating it again, you have a process problem. So I went back and I collected a small subset of the data. I built another model off of it. And it was very, very difficult to do this from a data point of view, just getting that data. And now I have two models that I'm showing you here. And basically what I want you to take away from the graph is the models are roughly the same. I could spend a year going and getting that data, but my model wouldn't be all that much better. So screw it. I'll move on and do something different. So this is what the types of things you want to get into your testing. What is worthwhile doing, and get data supporting whether that's worthwhile doing or not just, I think it's a good idea. So we're going to release simple models. We're going to learn from the model. We're going to take it back to experts, get their opinions, get feedback from our customers, and then we're going to repeat the entire process all over again. So this was my final model. A little bit of math porn, right? I did not start with this. I got to this point because I made probably 50 models. Remember the original model that I started with? It was just a couple of simple equations. But each thing I learned from, I gained a little bit more information, made the model a little bit more complex, a little bit more adaptive, and I used this process. So the first thing I did is I empathized. I then defined the problem in a way that was well posed or tame. I then ideated on the problem by talking to experts, reading literature, thinking about it, and doing that a whole bunch of times, talking to other people that are experts in other fields. Then I took that and I built a prototype. And I tested my prototype. And then I went back and I built another prototype and I tested it. And then I might go back and I might say, like, I need to rethink this problem. What I'm doing may not be quite right. Go back and then do the prototyping again and then testing. So in this workflow, you can always go back and skip steps, but as you move forward, you must complete each step in the sequence as you go along. So if you built some tests and you go like, hey, I think the problem is really bad, you need to go back, empathize again, redefine your problem. And this happens a lot. Like, you think you're doing the right thing and you go back and you change your mind. Don't be afraid to do that. Don't get locked into like, hey, we had this idea on one day, we thought it was important, and we went ahead and did it. So advice on how to launch your career. There is no single path into this field. You're starting to see data science degrees, but if you have backgrounds in other areas, figure out how you're going to leverage that into those different types of data science fields that I told you about. Fundamentally, we're scientists. We have to think and work as scientists. Don't train yourself to be an expert in a tool. If you're a hammer, everything's a nail, right? Being a hammer is a good thing to have, but you should be more than that. Fundamentally, you're a scientist. Go learn the right tools for the types of things that you want to do. So like a lot of people love to go learn neural networks. Neural networks are great, especially if you're in computer vision or automatic speech recognition. Outside of that, they're not that great. So if you want to go into those fields, that's the tool to go to learn. If you want to go and do general data science, neural networks is not the field to go. They're not the tool to go learn. Like, get really good at stats. That will help you a lot more. Get a solid thinking and statistical thinking, dealing with uncertainty, ambiguity. Everything in the world is a probability distribution in a statistician's mind. Learn to think about that. There is no cut and dry, everything's sort of a wishy-washy. I annoy people at work because I kind of give them an answer and then argue against it. Develop fundamental programming skills, but you do not have to be an expert unless you want to be like the machine learning data scientist. Then you need to be an expert, but most data scientists are meh programmers. So learn some Python, learn some R. I suggest you learn both languages. If you want to become a machine learning engineer or the machine learning data scientist, then Java and Scala and Julia and stuff like that are handy to use. Be able to communicate complex ideas. This is, I think, one of the big weaknesses that people have. Fundamentally, at the end of the day, my job is to influence without authority. That means I need to convince people of my ideas. I need to be able to tell them why I think I'm right. I also need to be able to work with them to figure out what the real question is that they're trying to ask, so that when I'm doing the define phase of my process, that I can coax out of them what the true question is that they're asking. Then I want to be able to get some experience working with real data sets. So in school, you always work with these nice, clean data sets. All data is really, really dirty. Even like Kaggle data has been cleaned up for you. Get experience working with real messy data, because that's where you're going to really hone your skills. Like I said, most of the time is cleaning the data and ideating around the data. Get used to working with data that just doesn't make any sense. Get comfortable clarifying problems. Push back on your boss when he's asking you to do something. Get really, really good at making sure what you're doing is the right thing, and it is your job to make sure that the question being asked of you is clarified and well posed. It's not your boss's job. And pick an area to become an expert in. So I started in web application security. There is like 5 of us in the world that are really good web application security data scientists. And now I am working at Alexa, and I'm getting really good at understanding third-party applications within the Alexa ecosystem. And I need to become an expert in that domain. You don't have to start there, but you need to focus on becoming that expert, because at the end of the day, you're going to be a trusted advisor, and you need to know what you're talking about, not just some stats or some machine learning models, right? The business analyst is an expert in business. That's why they're business analysts. There's also analysts, which are not experts in business. You want to hone in on some area and develop that expertise. And if you want to follow me on LinkedIn, that's my LinkedIn, or on the app for the conference, you can also connect with me. And we have time for a couple of quick questions.
Yeah. Thank you, John, for the nice talk, and thank you for listening. We have around 3 minutes for questions.
She's going to bring you the mic. Oh.
Thank you. That was great. Very interesting. You touched on this a little bit in your summary. Can you kind of unpack a little bit of the soft skills necessary for both institutional success within the organization and cross-organizational success for building a career?
So I think the big skill is to have people trust your opinion. A lot of the times you're going to be the only person in the room that really understands the data and really truly understands the problem in a way that is well posed. So to be able to communicate and work with people and push back and fight with them, but fight in a way that they respect the feedback that you're giving to them. So they tell you to do A, and you argue with them and tell them that you really need to be doing either A prime or B. And do that in a way that you're building their trust and not creating enemies.
Thank you.
Why don't you go ahead and ask your question? I'll just repeat.
Sure. What's your advice to people that are trying to get into the industry? Like you said, looking at LinkedIn jobs and internships, there's a whole different variety of types of data scientists, data analysts needed. I don't know which area to focus. All I have is my R and Python, my SQL, and my tablet on my resume. That's it.
Gotcha. So the question was, how do you get your first job? How do you, when you're looking at LinkedIn, all these different types of jobs, and you have some basic skills, how do you identify that job? So look at the types of different job categories that I outlined there and identify which one of those defines you. So what you described, it sounds like a data scientist generalist. So look at those types of things. Don't look for the jobs that require a PhD in CS. Right? That's probably not a good fit for you. Even if you got that job, you probably wouldn't thrive in it. What you want to do is look for a company that is generalist in nature. They have an analytics team that needs somebody to come in and help them make general decisions. You have your stats background, you have some R and Python, you're not going to be writing production level code for them. Look for those jobs that have those types of requirements, and then figure out what differentiates you, right? What you just defined was, I know some R, Python, and some stats. That's a tool. That's a set of tools. That does not make you a data scientist. That makes you a tool user. So what is it that you're going to bring to the table that's going to allow you to use those tools? Is it that you understand business really well, or you're an expert in that area of the business, or you communicate really well and you can work between the analytics team and upper management? So figure out where your specialty is and then target those types of jobs. One last question.
Yes. In regards to your current role, you mentioned previously that you were working on the cybersecurity space. Do they have you working on one problem the majority of the time, or do they have you bouncing around to many problems, many data sets?
Generally, many problems, many data sets. I tend to do better when I'm focused on one bigger problem, but you tend to be blocked a lot by access to data and stuff like that. So I usually have one large project and then several projects that are in various startup phases, because they can usually take a long time to go through the first couple of phases where you define the problem and ideate and stuff like that, and talking to the experts. So you can do that type of stuff in parallel.
Many different DevOps cycles.
Many different DevOps cycles on it, exactly. Thank you guys very much for coming out.